The rapid growth of cities presents a significant environmental challenge. Every day, vast quantities of wastewater are generated from homes, businesses, and industries. This wastewater, often called sewage, is a complex mixture of water and waste products. When released into rivers, lakes, or oceans without proper cleaning, it causes severe pollution. Organic matter depletes oxygen, harming fish and other aquatic life. Contamination turns precious water bodies into open sewers, creating foul odors and unsafe conditions. The health implications are immense as contaminated water becomes a breeding ground for dangerous pathogens like cholera, typhoid, and dysentery. Domestic sewage originates from our homes and divides into two categories: black water and gray water. Black water comes from toilets, human feces, urine, and associated sludge, rich in organic matter, nutrients like nitrogen and phosphorus, and high pathogen loads. Gray water comes from showers, baths, sinks, and washing machines with soaps, detergents, food particles, and other organics. Together, these streams form raw sewage demanding robust, effective treatment. Traditional plants are complex, expensive to build, and consume large amounts of electrical energy, especially for aeration. We need alternatives that are simpler, use less energy, and are more affordable, yet still clean water effectively, minimize waste, and recover resources. Anaerobic treatment offers a low-energy pathway that fits sustainability and circular principles, well-suited for warm climates where microbes work fast without external heating. By harnessing oxygen-free biology, anaerobic systems stabilize organics, reduce pollutants, and generate biogas energy, a paradigm shift. Sewage as a resource for health and environmental protection. At the heart of anaerobic treatment is a remarkable community of microorganisms working without oxygen. Anaerobic means absence of oxygen. Specialized bacteria and archaea thrive in oxygen-free environments. They cooperate in a complex food web to break down organic pollutants through distinct stages. First, hydrolysis breaks proteins, fats, and carbohydrates into simpler compounds like sugars and amino acids. Fermentative bacteria drive hydrolysis, setting the stage for subsequent conversions. Then acidogenesis converts these into volatile fatty acids, alcohols, hydrogen, and carbon dioxide. These intermediates feed methanogens, the slow, sensitive specialists often limiting the overall rate. In methanogenesis, archaea consume mainly acetic acid, hydrogen, and carbon dioxide, producing methane and carbon dioxide, biogas. Because methane is the main component of natural gas, captured biogas becomes a renewable fuel. It can power cooking, heating, and electricity generation, turning waste into energy. Microbes also grow as concentrated sludge, essential for treatment but produced in relatively small amounts. The process delivers three outputs: treated effluent with reduced organics, valuable biogas, and minimal new biomass. A design challenge is retaining slow-growing methanogens while wastewater flows quickly. The Upflow Anaerobic Sludge Blanket, or UASB, solves this by feeding from the bottom through a dense sludge bed. Granular sludge forms dense, fast-settling particles that retain active biomass. A three-phase separator at the top simultaneously separates effluent, retains sludge, and collects biogas. Methane and carbon dioxide rise and are captured for use. The expanded granular sludge bed, or EGSB, uses higher upward velocities to expand and fluidize the bed. Fluidization improves wastewater granule contact, enabling higher loads or smaller footprints. EGSBs excel on high-strength industrial wastewaters, where contact and compactness are key. Anaerobic filters retain biomass on packing media, plastic, rock, or ceramic, as attached biofilms. Upflow passes wastewater over vast surface area where microbes consume pollutants. Fixed media prevents washout, offering robust operation and simplicity for smaller-scale applications. Each design retains biomass efficiently, enabling high-rate anaerobic treatment tailored to local needs. Aerobic systems require continuous oxygen. Anaerobic systems operate without it. Aeration can consume 50% or more of a plant's electricity, making it costly. Anaerobic treatment generates biogas, turning plants into potential net energy producers. Each kilogram of cod removed can yield about 0.35 cubic meters of methane. Aerobic plants generate large sludge volumes. Anaerobic systems produce roughly 20 to 30% of that. Trade-offs. Methanogens are slow and sensitive, requiring longer startup and slower recovery from shocks. Anaerobic treatment removes most organics, but often needs aerobic polishing to meet strict standards. Energy: anaerobic low, potential producer; aerobic high, energy consumer. Sludge: anaerobic low, aerobic high. Space: high-rate anaerobic compact, aerobic larger. Startup: anaerobic months, aerobic weeks, best of both. Anaerobic first for bulk removal and energy, followed by aerobic polishing for final quality. Stable operation depends on carefully controlled conditions for sensitive microbes. pH is critical. Methanogens function best near neutral, typically between 6.8 and 7.2. If pH drops, souring can inhibit or kill methanogens and crash the process. Continuous monitoring and alkalinity control keep pH stable. Temperature governs reaction speed. Most municipal systems run mesophilic at 30 to 38 degrees Celsius. Thermophilic is faster, but less stable and more energy-intensive, suited to concentrated wastes. Microbes need nitrogen, phosphorus, and trace metals like iron, nickel, cobalt, and molybdenum for enzymes. Toxins or inhibitors: heavy metals, high ammonia or sulfide, phenols, chlorinated solvents can suppress activity. Know the wastewater and apply pre-treatment as needed to protect the reactor's delicate ecosystem. Anaerobic treatment removes the bulk of organics, but is rarely a complete standalone solution. UASB effluent often ranges 30 to 70 milligrams per liter BOD, while standards can require below 20 or even 10. Post-treatment removes remaining dissolved organics and suspended solids. It addresses nutrients like nitrogen and phosphorus that drive eutrophication. Further disinfection is often required for safe discharge or reuse. Where land is available, ponds and wetlands provide low-cost polishing of organics, nutrients, and solids with minimal energy. In dense areas, compact aerobic polishing, lagoons or trickling filters, achieves rapid, high-quality effluent. A hybrid approach yields top performance with far less energy than full aerobic treatment. Thousands of full-scale projects worldwide prove anaerobic technology's viability, especially in warm regions. India pioneered municipal UASB adoption, with plants along the Ganga Basin treating tens of millions of liters per day. Captured biogas powers equipment, cutting operating costs and boosting sustainability. Brazil's extensive experience refined designs and built confidence across Latin America. With careful design, diligent operation, and appropriate polishing, cities protect public health, restore waters, and step toward a circular, sustainable future.